Hello everyone, I'm Pranay, a postdoc at CMU, and I'll be talking about our work on federated min-max optimization. Uh, this is a joint work with Rohan, a graduate student at CMU, Dr. Gauri Joshi, a faculty member at CMU, and Professor Pramod Varshney from Syracuse University. So this is the outline of the talk. First, I'll give some background. Then I'll talk about a specific min-max optimization problem which we consider and the algorithms we propose. This will be followed by some theoretical results we have achieved, followed by a summary of all our contributions. So let's get started. First, I'll give a background of simple minimization problems, federated learning, and then introduce briefly min-max optimization. So as we all know, simple minimization problems form the backbone of modern machine learning. Uh, Usually we come across minimization problems of the form min of fx, where f can be either in the form of a expected value of a random variable, where d is the local data distribution, or it can be an empirical sum, where m is the number of training samples and we compute the average across all training samples. The most common algorithm used to solve such problems is stochastic gradient descent, or SGD, where at every iteration x is updated using a stochastic gradient of the function. So instead of computing the full gradient, we use a stochastic gradient. Federated learning is a distributed learning paradigm to solve these minimization problems. Here, n is the number of clients, and federated learning is characterized by infrequent communication between the n clients and the server. The data across all these n clients can be heterogeneously distributed. And one of the crucial aspects of federated learning is preservation of client data privacy. So the clients do not need to send their actual data to the server. One of the most commonly cited applications of federated learning is predicting the next word in smartphones. But the question is, can simple minimization problems encompass all the problems we encounter while doing machine learning? So to address some of the limitations of simple minimization problems, we study min-max optimization, where we have min over x and max over y of a function, which is a function of both x and y. And some of the applications of min-max optimization are GANs, adversarial training of neural networks, and reinforcement learning. In many of these modern applications, f is often non-convex in x and non-concave in y, which makes the problem even more challenging. Let's look at one of the very concrete applications of min-max optimization, which is generative adversarial network. Suppose we have a neural network, which we call the generator, which desires to take some boring random variable, say a d-dimensional noise vector, and produce some fake images. Now, these fake images have to mimic the images generated in the real world, right? So this is the task of the generator. At the same time, there is a discriminator which wants to find out whether an image is generated from the real world or if it's a fake image, right? And based on its input, the generator produces a predicted label which assigns how likely is it that the input image is a fake versus a real image. Now, as you can guess, the problem for the generator and discriminator are conflicting. Generator wants to generate an image which is fake, but as closely mimicking a real image as possible, while the discriminator wants to discriminate real images from the fake ones. Mathematically speaking, if we denote the parameters of generator by x and the parameters of discriminator by y, then the utilities of generator and discriminator are opposite of each other. They are negative of each other. So what the discriminator wants to do is assign a higher weight, a higher score to an image generated from the real world, while assign a lower score to an image generated from by the generator. And looking at this perspective, the resulting problem we get is a min-max optimization, where The problem is min in X and max in Y. Next, let's discuss the specific problem of min-max optimization we consider and the corresponding algorithm we have proposed. So the problem we consider is min over X, max over Y of F, where F is the average of n functions. Here n is the number of clients, and each of these n functions, Fi's, corresponds to the ith client. Therefore, it depends on the local data distribution at the clients. The algorithm we use is called local SGDA or stochastic gradient descent ascent, where at each client I, the X or min variable is updated using a stochastic gradient descent step, while the max variable Y is updated using a stochastic gradient ascent step. And notice that the directions are unbiased estimators of the true gradient, and they have bounded variance with respect to the true gradient of Fi's. Once in a while, say every tau iterations, the clients send their X's and Y's, their local X's and Y's to the server, which averages them and returns them to the clients. And from these new averaged values, the process at the clients restarts. So let's look at some of our theoretical results. We assume that all the local functions Fi's are smooth in both the X and Y variable. We also assume that the local gradient Fi is in a bounded distance of the global gradient F. We first assume that the global function F is non-convex in X and strongly concave in Y. We have already assumed that it is smooth in both X and Y, right? So in this case, if we define phi as only the function of X, that is the function we achieve after performing the maximization operation, then we define an epsilon stationary point as a point where the expected value of the gradient at this function phi is smaller than epsilon. This is how we define an epsilon approximate stationary point. And to achieve such a point, the sample complexity is given by order 1 over n epsilon to the 4 per client. So this is the computation which every client needs to do. This is the maximum computation which every client needs to do. Notice that there is n in the denominator. This means that as the number of clients increases, the computation each client has to do goes down. This phenomena is known as linear speed up in the number of clients in literature. Also, our result is optimal in epsilon. This cannot be improved further. The number of communication rounds we require, that is the number of times the clients need to send their X's and Y's to the server, and which the server computes the average of and returns. The number of times this back and forth has to happen is order 1 over epsilon cube. Now notice that this is smaller than the total number of iterations the algorithm has to perform, right? Let's compare our results to some of the existing work. When it is non-convex in X and strongly concave in Y, the first paper to consider this problem was Lin et al. In 2020. And although their result was optimal in epsilon, but they required a batch size which increased with epsilon. So they couldn't use a constant batch size. Deng et al. Considered this problem in the federated setting. However, their result, as you can see, is suboptimal in epsilon. Compared to these, our results are both optimal in epsilon, as well as our algorithm works with a constant batch size or order 1 batch size. In addition, we also achieve a linear speedup with increasing number of clients. Let's look at another class of functions. So again, we assume all the local functions are smooth in both X and Y. Again, we assume that the local gradients, grad Fi's, are within a bounded radius of the global gradient, grad F. Now, instead of assuming that the function is strongly concave in Y, which we assumed in the previous class of functions, we assume that the function is just concave in Y. It stays non-convex in X, but the function is now concave in Y, right? So we are considering slightly larger class of functions. Again, we define phi as the function we achieve after performing the maximization operation. Now notice that because the maximization problem is no longer strongly concave, so the maximizer of f with respect to y is no longer unique. It need not be unique, right? Therefore, the function you get after performing the maximization operation, that is the function of x, which you get phi, this need not be smooth anymore, right? This can be non-smooth. Therefore, we have to modify what we did so far. So phi, the maximization, the result of the maximization operation is potentially non-smooth. Therefore, we define an alternate notion of stationarity. So now we define epsilon stationary point as a point where the expected value of gradient is smaller than epsilon, but we are considering gradient of a different function. Instead of phi, we are considering phi of lambda. This phi of lambda is a smooth approximation of phi, right? So it's a smooth function which approximates phi in some sense. And with this approximation, we can show that the sample complexity required to achieve an epsilon stationary point is order 1 over n times epsilon to the 8 per client. So this is the maximum computation every client has to do. Again, because of the n in the denominator, we get a linear speedup in n. The number of communication rounds required is order 1 over epsilon to the 7. Again, you see that we don't need to communicate in every round. We can communicate infrequently and still achieve convergence. Again, comparing our result with some of the existing work, Lin et al. Was the first work to consider this non-convex concave class of functions, and this was their sample complexity. Deng et al. Considered this problem in a federated setting, but their sample complexity was way too suboptimal, and this was the communication cost they required. Compared to these, our work achieves a better sample complexity compared to Deng et al., while it also achieves linear speedup with the number of clients. And we, as you can see on the right, we achieve communication savings as well. But the question is this sample complexity optimal in epsilon? And this is so far an open problem. Just to summarize, we have considered this federated min-max optimization problem. Here, n is the number of clients and fi are the local client functions. We have considered these classes of functions. All the classes of functions are non-convex in x, but they can be strongly concave in y, PL in y, concave in y, or 1-point concave in y. So as you go down the list, the class of functions becomes more and more general. In this presentation, we only talked about strongly concave and concave settings, but we have considered all these 4 classes of functions. Our algorithms are local updates based. All our algorithms work with a constant order 1 batch size. Our sample complexity results are optimal for the classes of functions shown in blue, namely strongly concave in Y and Polyak-Loyasevich in Y. And our sample complexity results are state-of-the-art for the classes of functions shown in red. That is, if the function is concave in Y or 1-point concave in Y. For all our algorithms, we achieve a linear speedup as the number of clients increases. So the computation which every client has to do decreases as you increase the number of clients. Thanks for listening, and you can find more details on our paper on arXiv, and I look forward to answering all the questions you might have in the virtual session as well as the on-site session. Thanks.